Okay, so hello again. I hope you enjoyed the coffee break, and now you are energized for the second part of this morning. So we are going to have a talk by Dr. Sivan Trajtenberg-Mills, who recently was hired by my department. She's going to talk about optical technologies for quantum computation.
So hello everyone, my name is Sivan Trajtenberg-Mills. I'm recently here in Tel Aviv University from the Electrical Engineering Department. I'm here to talk to you about optical technologies for quantum computation. Specifically, I'll be discussing two projects, one on continuous variable quantum secure multi-party deep learning, and the other about high-speed spatial light modulators. This has been great talks today, and some of the previous talks already laid the foundations of things I'm about to say, so it's going to be nice. So following Yaron Oza's wonderful introduction, he said, you know, we're in this quantum revolution. What is this quantum revolution we're in? They say we're in the third quantum revolution. Why is it the third? So, you know, in 1900, Lord Kelvin said there is no new physics to be discovered, following, of course, by what we call the golden age of physics and the first quantum revolution, which was really about understanding, about laying the foundations to this new physics and understanding the whole foundations of quantum mechanics. Later on, at around the 80s, people started thinking, okay, well, what can we do? Having known all of this great theory, can we use these quantum particles to do useful things? So Richard Feynman was the first one who coined the term a quantum computer, and later more theory work came about how you can use these quantum entities in order to do useful things, and experimental work started coming up about how to control these quantum entities, and this was what we call the second quantum revolution, which was all about control. And today, when we look at what's happening today, now it's all about scaling. We know the fundamentals, we know how to control them, but how do we scale this up? We know this is an extremely useful technology, but how do we scale this up into something really big that can really help humanity? And this is where we're at today. So why is this scaling problem so hard? Well, as a fundamental thing, well, first thing, we can't even agree on what the technology should be for quantum computing. Some people think it should be photons, some people think it should be trapped ions. Google is putting their money in superconducting qubits, and here at Tel Aviv University, we also have the IQCC in collaboration with Quantum Machines that has a superconducting quantum computer. And the new kid on the block showing really competitive metrics now is cold atoms for computing, and you know, billions of dollars have been spent on all of these technologies, and not only in industry but also in academia, and not only for quantum computing but also for quantum sensing and for quantum communications, and where quantum sensing can allow super resolution and enhance sensitivity, and also for quantum communication. So my question to this is, can optics help in this quest? You know, it's a very multi-dimensional problem with lots of aspects to it, and can we do something with optics to, you know, bring this up to speed? So, well, the first obvious answers, well, you already told us that photons can be used for quantum computing, right? And yeah, indeed, you know, they're robust to noise and apparently scalable, but, you know, photonic quantum computers have yet to show large-scale demonstrations like their counterparts. But the place where photons really shine is with quantum communication, where, you know, they are the ultimate winners. Maybe because we already use light in the internet. We already use light for communication. The infrastructure is there. They travel at the speed of light inherently because they are light. So there it is. So there they're really the ones who win. And indeed, quantum communication has been shown through optical fibers and on satellites, and you can go ahead and buy, you know, QKD systems today, and China has been saying that it has over thousands of kilometers of secure quantum links already today. So also thanks to the previous talks who discussed quantum security and quantum key distribution. I don't have to go too much into this, but just so that we're all up to scale. So quantum key distribution allows the sharing of a secret key between two parties. The first, maybe the most famous protocol, BB84, who showed how to do this with single photons. So you use single photons, you encode zeros and ones on these single photons. It allows you to have security and to share a secure key, but it really requires, dedicated equipment and really taking photons and discretizing them for the 0-1, for a digital kind of key distribution. So and you can go ahead and buy these type of systems today. Another kind of quantum key distribution is a generalization of this discrete quantum key distribution to an infinite dimensional space. It's called continuous variable quantum key distribution, where instead of sending single photons that represents zeros or ones, in CVQKD you encode the information in a continuous distribution of light, that is on the quadratures of light. The quadratures of light obey the uncertainty principle, and this is in shot noise units. So if you want to look at the quadratures of light, you can't pin it down to a single point. They always have some distribution about them in shot noise units. If you send this weak coherent light over some link, the link will always add some noise, and you can estimate the amount of noise that is added by the link. And after you measure these quadratures, if you know the parameters of the link, then you know the amount of added noise that should be there, and if there's any additional noise, then you know that an eavesdropper has gotten to your information, and that's basically on a very high level how you ensure security. But another revolution that's happening right at the same time, and I think also in Cyber Week at the same time, is the AI revolution. So, this is maybe something that has reached more people, and everyone know and use AI today, and also awarded by the Nobel Prize lately. And how does this AI work on a very, very basic level? So you have some vector X, and this vector X could be, it could be text, it could be an image, it could be audio, it could be anything, and you want to estimate some output, some function of this vector, and the way you do it is you run it through a network that has many hidden layers. What these layers on a very high level do, they have weights, which they have to multiply this vector by these weights, following by an activation function. So you have lots of weights, and you multiply. So you really, in order to do this type of computation, you have to know how to do vector matrix multiplication followed by an activation function. You have to do this a lot of times. Now, this idea is not new, but it only started being useful the minute the amount of weight started to grow. So while the idea is around since the 1950s, we never had the amount of compute to actually do something useful about it. But now, with the amount of weights being much over trillions of weights, allowing for amazing models like GPT-4 and Gemini and whatnot, we really see how this can work. But the problem with having so many weights is that it demands using a cloud. It demands using big servers that can handle this amount of compute that can handle these amount of weights. And so it really, it means that we have to have some sort of cloud that's gonna keep all this compute. So we're gonna discuss a cloud where there's servers who have these weights and edge devices that might be smaller devices with minimal memory. They could be drones, they could be cell phones, they could be home computers, they could be even smaller devices. So just edge devices. And the minute you have this distributed kind of computing, then this raises the issue of security. So in this multi-party computation problem, what we have is a server that has the weights in the cloud, and we have a client that has the vector x, the information, and he wants to compute some sort of function with the weights, so in order to make some sort of predictions. So the client might have a vector that represents private medical information, for instance, that he doesn't want to share with the server, but he does, so he has a secret vector x that he doesn't want to share, but he does need to compute a deep learning task that requires him to be able to compute w times x, the weights times x. And then we have a server who has this vector w, but he also doesn't want to share it because that's his IP. So he doesn't want to share this vector w, and he doesn't want x to know the w, but he does need to allow the client to compute w times x. So the question is, can we find a protocol that can allow both the client to keep his vector x secret and the server to keep his vector w secret, while allowing the client to perform the compute that he wants. So my colleagues at MIT developed a theoretical framework for this. So the server basically will encode the DNN weights onto the complex amplitude of some coherent state. Some magical unitary transformation will happen that will yield the desired calculation, and then the client will perform a measurement and feed forward. This measurement and feed forward will inherently add some excess noise to the state, just like in CVQKD, and the client will return a state to the server for a security check. So how do we implement this using light? And I'm going to go slow. So first thing, you can theoretically calculate what the leakage will be for the weights and for the vector x, and you can also see what kind of accuracy you can get for MNIST classification task on this. But how do we implement it? Okay, so here I come in. So, okay, I'm going to go very slowly along these paths to show you how using standard optical devices that are out there and every CVQKD uses, and they're used for telecommunications, they're not specialized in any way, in order to implement this. So we start with the server. The server has to take vector w, which, so maybe I'll say that x and w for this type of task are real valued, while for CVQKD we need complex valued vectors. So we use this type of encoding in order to encode these real values on complex valued vector x and w. And the trick that we're running here is that the complex vectors and the real vectors have the same inner product. And that's really the important part, because what we want to compute is the inner product. So if they have the same inner product, we're happy, and we can, this is just like an easy math to show intuitively why this works. And so the server is going to take this complex now vector w and going to use an IQ modulation of the DNN weight onto a weak coherent state. So just taking a laser, attenuating it so that there's very weak pulses with about 1 photon per pulse, and then putting this vector w into the coherent state. So this is, if I look at the real part of w and the imaginary part of w, it has some distribution. And then sends it over to the client. The client takes this vector w, passes it through a Mach-Zehnder interferometer with 2 phase shifters, and if he can determine the phase in these phase shifters in a very specific way that has to do with his vector x, then the output will be a vector with element-wise multiplication of each of the input vectors. That is, if the input was this vector w and it has pulses, you know that each pulse represents one of the weights, after this Mach-Zehnder interferometer, each element of the vector will be the multiplication of what we put inside. So technically now, okay, if the client could just integrate this, he would have the result of x.w, exactly what he wants. But if he integrates on the whole thing, well, then he has all the information. We don't want that. So we have to find a trick of him being able to take just a little bit out of this vector, just a tiny, tiny little bit, to minimally disturb this state in order to not learn a lot about the vector W, and also, certify that he didn't learn much about this vector. So how does he do this? Up here, I've just written the definition of a discrete Fourier transform. You might recognize it. It's just a definition of what a discrete Fourier transform looks like. So if we just plug into this discrete Fourier transform this input vector, so you have to put, and we look at the zero order of it, so k has to be 0 in this equation, and each of these vector elements is wi times xi. So if we just plug it in, we see that the zero order of the discrete Fourier transform is exactly w times x. Amazing. So if we could take just the zero order out of the Fourier transform, that's enough information to be able to calculate your deep learning computation, everything that you need. Physically, it's a little harder to do, but in optics, we do have ways of doing something close to that. That is, if we had a series of time pulses in the frequency domain, we can look at it in the frequency domain. It will look something like this. If I zoom in a little bit, I can put a filter, an optical filter, in order to filter out just the zero order, and I'll get something very, very small, and I can transmit everything back. So the client will pass it through a very narrow filter, which will give him, the exact result that he needs in order to perform this calculation, and he will measure it using homodyne detection, which allows him to read out the real part, which is what we need for the calculation, and everything else is going to be reflected back. And this is also an important part, because this is what will allow the server to know that the client didn't take more than he needs. So the whole thing is reflected back. The client can put it through another Mach-Zehnder interferometer, which reverses what he did in the first place to get this new vector W prime, which should be very, very similar to the original vector, because we took very little out of the vector itself. Give it back to the server that can beat it against, because he knows what he sent, he can beat it against what he had, and check indeed that the client didn't take too much. We can calculate the transmission and the added noise, also as a function of alpha, which is the amount of photons, the photon occupation. And we can calculate the information leakage, so how much information, an upper bound on how much information could have been leaked in this way. And we see that it really has to do with the bandwidth of our filter and the bandwidth of our modulation, which makes a lot of sense, right? We really needed just the zero order, but the amount of information that will leak has to do with how much I took relative to how much I encoded. And that's what we also see through simulation, and we're currently working on an experimental demonstration on this with our collaborators at CNRS. But can we do things? So I showed you one thing that we can do, but can we do more for computing using optical technologies? Well, in order to understand how we can do more, then we first have to understand how qubits are controlled today. So this is a recent picture from a really great experiment showing over 6,000 atoms trapped, atom traps. And so you can really see like individual atoms trapped in an atomic quantum computer. Ions kind of look like this. Solid state kind of look like this. So what we notice in all of these type of quantum computing platforms is that the qubits are spatially separated. Right, they're like little dots that are spatially separated, and the programming of these computers is using light. So you take light pulses and you shine on these spatially separated qubits. So we kind of understand that if we want to control quantum computers, we need light. We need light that we can spatially control. Many of these computers suffer from short coherence times, and generally, we'd like to have a fast clock to be compatible with electronics. So I'll take a step further and say that in order to control this type of quantum computers, you need to spatially control light at high speeds. So how do we control light today? Like, how does that even work? Do we know how to do it? Well, of course, I told you we use the internet. It has light that we control. We can encode stuff on light. And that's typically done using electro-optic modulators. They can work at gigahertz speed, but they have no spatial control. So it's just like a single pixel that you can modulate at very, very high speeds. If you want to go to something a little slower, that allows a little more pixels, you can do acousto-optic modulators or acousto-optic deflectors. They're one-dimensional, so they allow basically to shift the laser beam using an acoustic wave. So you can control a beam with some restrictions in one dimension. You can stack one on top of the other, and then with two, use two, and they can go up to megahertz speeds. If you want to have like a lot of, control a lot of degrees of freedom, you can use something called spatial light modulators. These are devices that can spatially control the phase or amplitude of light. So light comes in, it has millions of pixels. Each pixel can change the amplitude or the phase. They return and get that extra amplitude or phase. And in fact, the projector that's projecting this presentation on the screen has a spatial light modulator in it, modulating the light so that you can see this presentation. They're extremely useful devices. They're used for adaptive optics in space, optical tweezers, multiplane light conversion, super-resolution microscopy, high-dimensional qubits, quantum computing. I use them in my works for nonlinear holograms, neural networks, cavity array trimming, and many, many, many more. So what's the problem with them? Well, they're very slow. Very slow, that is slower than kilohertz rates. So how slow is slow? You could use liquid crystal on silicon devices, which are very, very popular, huge apertures, millions of pixels, tens of hertz, very slow. You can go a little further with binary amplitude control with micromirror devices, go to kilohertz speeds. If you want to go as fast as you can always use your electro-optic modulators, but that's just a single pixel. The AODs don't have real control of the entire field like SLMs do, but they are used for atomic quantum computers, so I'm just going to put them out here for reference. And people have been researching great platforms using nanophotonics in order to solve this problem. So they don't have many pixels, but you could say, but they always claim that they're very scalable. But there is a more basic problem to their scaling, and that is that they all have this 2D architecture. And when you have a 2D architecture with many devices, you have to wire a wire to control each of the devices. And then how will the scaling work? What is the scaling limited by? Just the amount of wires you can fit. So if you know the area that you can put devices in and what the spacing between the wires is, which will always be finite, then you can just calculate what the maximal amount of devices that you can fit is, and this is fundamental. You can't do anything about this if you don't change the architecture. And if you put in realistic numbers in here, then you get that the amount of devices that you can fit is about 400. So, and it always looks like a disaster. So here I'm plotting in blue kind of the up to 400. That is that all of these very high-speed devices, this is the area they can't penetrate unless they change their architecture. So if you want to go from blue to white, you have to change your architecture. You can't be in a 2D architecture like wiring scenario. And if you want to go for larger devices but higher speed, you have to find a fast physical response. You have to find something that responds fast enough. So for this work, we thought of, what's the fastest physical response we could think of? Oh, let's use the same one that electro-optic modulators use. That's the electro-optic effect. It's very, very fast. And we want a different architecture, so what's the largest architecture we could think of? Oh, well, that's CMOS. It's used in cameras today. It's used everywhere, and it's not 2D. Oh, wow, how hasn't anyone thought of this before? Well, the problem is that the effect is very, very small. So how do we enhance a very small effect? What we chose to do is, instead of controlling the phase or amplitude of light, going as it propagates, then we will use a resonance. So let's take a resonance, and we'll shift the resonance around, and by shifting the resonance around, we will get a coupled phase and amplitude response. Still, it'll be just 1 degree of freedom, but it'll be coupled phase and amplitude response. And since I just have to move the resonance a little bit in order to get a very large response, this is how this is going to allow us to take a small response and make it larger. So we chose to use a guided mode resonance. This is just a resonance that arises from a light traveling through some sort of slab. And we used an EO material, electro-optic material, thin film lithium niobate. It's very popular. We used a grating, a silicon nitride grating, in order to couple light into this guided mode. By controlling the parameters of the grating, you can control the parameters of your resonance, how wide it is, where exactly it is. We chose it to be in the telecom wavelength and to have a Q factor, a quality factor of about 1,000. How do we increase it, this electro-optic response, to be really, really strong? Because again, it's a very small effect. We can basically, by maximizing the field overlap, intuitively meaning more field inside the material, the active material, will give you a larger response, and this is the math that has to do with it. So by designing these to have a very high field overlap, we'll also get a stronger response. And you know, if we want to show this against other works, having a higher Q and higher field overlap will give us this stronger response. And so okay, so this is the architecture that we're going for. We're going to have a CMOS backplane that has millions of pixels. We're going to buy it from a company. It's commercial CMOS backplane. We're going to have our electro-optic material, thin film lithium niobate. We're going to put a silicon nitride grating in order to make sure we have a guided mode inside, which is going to give us our resonance. You know, we're going to fabricate this and see if it works. So we started by fabricating just one crystal and measuring how the resonance moves around as we apply an electric field, and we saw that indeed we can get resonance shift. We can do a few pixels and see what it looks like, and we can, you know, modulate the light in the far field with just a few pixels. We can measure how fast this is, and here we used a detector that has a bandwidth of 1.6 gigahertz, and this is the result of our measurement, which basically means that we were limited by our detector, but it's a minimum of 1.6 gigahertz is the bandwidth. And okay, but then we want to scale it up. So in order to scale it up, we need a very large grating. So we used interference lithography in order to get very uniform, very good, very large grating. We continued to develop a fabrication process for bonding this whole thing, and we bonded a full device. We could measure the resonance on it, we could model it, and then when we came to measure you know, the modulation in the far field, we couldn't measure anything. So we went back to the drawing board and saw, you know, and we could calculate the parameters based on the voltages that we had, and, you know, all the parameters of the materials. And we saw that, oh, well, we probably shouldn't expect to measure anything, because the effect would be very, very small, even though we ran all these tricks. So we calculated what we had to do in order to make this a useful device, basically get a higher Q, use better materials, and there we showed that we could get significant improvement. So what I showed you is our work. So we're up there at the gigahertz speed, very, very, very fast in an architecture that is scalable, an architecture that could go to millions of crystals. By using a different material, higher speed electronics, and higher Qs, we could make this into a useful device. And I'd like to thank my collaborators from MIT on this. And so just to conclude, I've discussed today optical technologies for quantum computation, different fields, different things that you could do using light, both high-speed spatial light modulators, a bottleneck today for many advanced quantum technologies, and also continuous variable quantum secure multi-party deep learning for security using existing CV QKD hardware. With that, I'd like to thank you for your attention.